Welcome, students. So let's start with the quote, vector calculus, the final frontier. These are the voyages of MATH251 Enterprise. Its a 4-month mission to explore strange new calculus, to seek out new geometries and new integration techniques, to boldly go where no Calc 2 student has gone ever before. Okay, so of course that's from Star Trek. Anyway, so let's start with today's lecture, 16.1. We want to discuss about vector fields. So what are vector fields? So consider the following. So you have a subset D of R2. So you have a subset, some subset of D of R2, and you're defining a function f from this D to space of all 2 by 2 vectors. Sorry, not 2 by 2 vectors of dimension 2, then such a function is called a vector field. So the idea is you are assigning to every point in R2 a vector in V2. So you will have two components. So essentially, if you have f of xy, so you have f, a function, this will be some vector f1 of xy. Then the second component will be f2 of xy. So now, why is this concept useful? Why do we need vector field? One example is over here. So these are, so for every point here in the space, you're given a vector associated to that point. All right. So this is an example. So this is an application example. Essentially, these are the water currents at 5 meters depth. And you can see the direction of the water current is given to you. So at this point, the water current is in this direction, and the length of this vector indicates the magnitude of water current. So this pictorial representation gives you a lot of information about basically the currents, right? And the magnitudes are colored here. So the blue color ones and so you can see the colors so that you can make sense of how the currents are in which direction and what is the strength. Okay, so vector fields are essentially quite, so drawing vector field is quite an interesting information you can use to interpret a lot of phenomena. Okay, similarly, if you look at the magnetic field, so if you have South Pole and North Pole here, and suppose you place, then the vector field will be vector field. This is, in this case, it is the magnetic field magnetic field, which is a vector field, will have the following shape. That means at this point, the magnitude will be given by the length of it, and the direction is also given to you. So you see, vector field tells you exactly how the magnitude of field is, or vector is, at each point, and also the direction. Very useful information. So let's see, look at this vector field f, which is yi plus xj divided by square root of x squared plus y squared. It is shown in the diagram here. Of course, you are given only a few of them, not all of them, and you want to basically draw the vector field. So how do we go about it? So let's look at, say, let's match these. So what is f of, say, 1, 0? F of 1, 0 is essentially minus 0i plus x, which is 1, j divided by square root of 1 square. So it's essentially j. So the way you draw it is as follows. So you go at 1, 0, and then you sketch the vector j. So vector j is a unit vector in the direction of y-axis, so you'll get that. Okay. Similarly, let's look at f of 2, 2. So f of 2, 2 is going to be minus 2. So we get minus 2i plus 2j divided by square root of 2 square plus 2 square. So that is going to be 2 over root. So 2 over, so this is going to be 8. So 2 root 2i with a minus sign plus 2j over 2 root 2. So in this case, you get 1 by root 2i with a minus sign plus 1 by root 2j. So you basically go here 2, 2, and then you draw a vector. So you're going basically minus 1 by root 2 in I direction. So this way, negative direction for minus 1 by root 2, and for j you have 1 by root 2. So essentially you can think about it, the way to think about this would be to look at this vector as a resultant of these two vectors, right? So similarly you can plot the whole vector field. Okay. Now similar thing can be generalized in 3 dimensions. So let E be a subset of R3. A vector field on R3 is a function f, which assigns to every point x, y, z in E a 3-dimensional vector f, x, y, z. So the idea is you have a function, so you have a subset of E to R3. E is a subset of R3. Then your vector func field is basically a map from E to V3. This is set of all 3-dimensional vectors. Okay, so some of the examples are given to you here. So at any point you have a direction. So this is how you sketch the vector field. All right. So one of the interesting example is the following. So assume an object of mass m is located at origin in R3. So you have an object of mass m located at this. Then the gravitational force, let point mass m be posted here, located here. Then because of Newton's law of motion, of gravitation, sorry, not motion, Newton's law of gravitation, there will be a force acting on this. And that force, gravitational force at this point, P, is given by f of x, y, z as minus m mg upon length of vector x cube times vector x. So essentially you can think about this as minus mmg upon, so if you have x, y, z, so if you're using that, so it'll be x squared plus y squared plus z squared times vector x, y, z. Okay, so this is a vector x. It's a different vector altogether, all right? So it has no connection with this x, except for that is a component. So if you think about it, how do I interpret this? And again, it's power 3 here. So essentially, I'm dividing by the length of it. So the smaller the length, if I'm taking cube, so you'll see that the force will be higher when it's less than 1. So this is how the force will be acting. But if you're farther, the force will be smaller. Yeah. But if you're closer to the origin, the force will be bigger. So why? Because you're dividing by a number. If this number is less than 1, the magnitude of a vector is less than 1, then dividing by that will basically make it big. Okay. So that's the idea. So we have the following. So you see there is an application of vector fields even in the gravitational setup. Okay. So now this gives a idea. We'll see the connection in a moment. So what is a gradient field? Gradient field is the following. So let's take f a scalar function of 3 variables. That means what? F is a function from some subset D of R3 to R. Then gradient field, which is grad f, we have already seen that is fx, fy, fz, right? So if you write it in the ijk form, it's going to be fx, xyi plus fy, xyj, fz. That means you take x derivative of y derivative and z derivative and organize them in the following way. Now, consider the following. Find the gradient of the following scalar function. So this is a scalar function. So let's find the gradient of this. So in this case, grad f is going to be, I'm going to use the, so partial derivative of f with respect to x, partial derivative of f with respect to y, and partial derivative of f with respect to z. So the first one, the partial derivative. So I can write this as x square plus y square plus z square to the power minus 1 over 2. So this is going to be minus 1 by 2 x the power minus 1, so minus 1 by 3. So it's essentially going to be x square plus y square plus z square square root to the power 3 multiplied by derivative of inside with respect to x, which is going to be 2x. Now note that this equation is symmetric in y and z. So if you take partial derivative with respect to with respect to y, you will get the same thing, but with what? You get 2y upon 2 x square plus y square plus z square, the whole power 3. And we get minus 2z upon 2 square root of x square plus y square plus z square. So this is my gradient of the scalar function here. All right. So now we call a vector field f is called conservative vector field if it is a gradient of some scalar function. That means there exists a function f such that f equals to grad f. Okay, so this capital vector function is equal to the grad of some scalar function. In this situation, this small f is called the potential function. All right. So now the question is the gravitational field, which is given by f equals to minus mg length of x vector x cube vector x, is this function, is this vector field potential? That is, does there exist f such that your vector field f equals to grad f? So this, if this happens, then we can say, if we can find such an f, we can say that your gravitational field is a conservative vector field because we found out a potential function for it. So towards that, notice the following. So we have, so these are the constants, right? So let's ignore that for a moment and we can work on the following. We can look at, consider the following function. So let's look at the function f of x or equals to f of vector x, right? Or if I want to write it as f of x, y, z equals to 1 by square root of x square plus y square plus z square. So we have f of x equals to this. We have already seen what is grad of f. Yeah, we have already seen that here, right? So grad of f is essentially, if you cancel out all things, you get minus x, y, z divided by 1 by square root of x squared plus y squared plus z squared to the power 3. This can be written as minus 1 by, if I choose to call this as vector x, yeah, then this is going to be length of vector x cubed times vector x, right? So if I take this as 1 by length of vector x, then I found out from the previous example, grad f is going to be minus vector x over length of x cubed, right? So if I had the constant multiplied, so this means if this is my, so if I call this as say f naught here, so what do I have? I have, if I take f to be minus mmg f naught, then what do I get? Grad of f is going to be, constants come out of the integration, differentiation, right? We have, because these are constants, grad of f naught, then we get, this is same as g, grad of f naught turned out to be what? Minus x cubed. So let me put that minus sign outside. So I don't even need to take minus, I need to take plus of these, right? So plus of this, this will give me already vector x over length of vector x whole cube. So essentially, then we have f is conservative, right? Why? Since f equals to grad of a scalar function. Let me write down that scalar function, grad f, where f equals to m g over length of vector x. So this was a discussion about vector fields. Now we'll move on to line integrals. Okay, so that's the next interesting concept. Thank you for your attention.